Welcome to The Explainer. I'm absolutely thrilled to be your virtual chemistry tutor today. Even really experienced chemistry students can completely trip up on foundational calculations. If you're already pretty comfortable with the basics, but you want to fine-tune your quantitative chemistry skills, optimize your workflows, and just build a rock-solid, error-free foundation for your advanced chemistry journey, well, you are in the exact right place. Today, we're moving way beyond just memorizing formulas. We're going to look at the deeper logic of how molecules are measured and managed. So, here's a question for you. Why do so many students lose points on chemistry exams before they even finish the math? Honestly, it's a tragedy I see all the time as a tutor. A student will have absolutely perfect chemical logic, right? They'll map out this beautiful, complex multi-step synthesis, but it gets completely ruined by a tiny foundational measurement error right at the very start of the problem. If your initial assumptions about precision and ratios are wrong, well, the most brilliant stoichiometry in the world just won't save your final answer. But don't worry, we are going to fix that today. Okay, here's our quick roadmap for today's session. First, mastering significant figures. Second, finding the empirical formula. Third, mixing it up with concentration. Fourth, we'll look at a concentration comparison table. And finally, number 5, beating the exam clock. Let's dive in. Section 1. Mastering significant figures.
Okay, let's rapid fire the 4 core rules to refresh your baseline. First up, non-zero numbers are always significant. Second, sandwich zeros. The ones trapped right in between non-zero numbers, those are significant too. Third, left side zeros are not significant. They're literally just placeholders that don't indicate any level of precision whatsoever. And fourth, right side zeros are significant, but only, and I mean only, if the number has a decimal point. Now, as an advanced student, it's absolutely crucial to remember why these rules exist in the first place. They aren't just arbitrary hoops your teacher's making you jump through. These rules exist to ensure we never claim more precision on paper than our physical laboratory instruments actually gave us during the experiment.
Let's actually put that last rule into action to see the mathematical reality of your measurements. Take a look at the number 0.200. Because of that specific decimal point, those trailing zeros absolutely count, giving the measurement a really high level of precision with 3 significant figures. You're effectively telling everyone that your instrument was accurate right down to the thousandths place. But what about the number 200 without a decimal? It only has 1 significant figure. That means very low precision. You're basically implying the real number could be anywhere from 150 to 249. Literally, 1 tiny decimal point completely changes the mathematical reality and the implied tolerance of your entire measurement.
Moving right along to Section 2, finding the empirical formula.
So, by definition, the empirical formula is the simplest whole number ratio of the various atoms present in a compound. I always tell my students to think of it as the most reduced, stripped-down ingredients list of a molecule. For example, while a biological molecule of glucose actually contains 6 carbons, 12 hydrogens, and 6 oxygens to function in the real world, its empirical formula simplifies that whole ratio down to its absolute core essence, which is CH2O. Now you might be wondering, why do chemists even care about this stripped-down version? Well, because when you run an unknown substance through a mass spectrometer, the machine doesn't just hand you a neat structural blueprint. It simply outputs the raw mass ratios of the elements. So finding the empirical formula is really your very first step in translating that raw data into an actual chemical identity.
Let's walk sequentially through my foolproof 5-step method for this, and let's really focus on the logic behind the workflow. Step 1. Write down the element percentages given to you. The mental trick here? Just assume you have exactly a 100-gram sample. That instantly turns those percentages into standard grams. Super easy. Step 2. Divide each of those by the element's atomic mass to get the moles. This step normalizes your data from, arbitrary weights into an actual count of atoms. Step 3. Look at your results and divide all of them by the smallest mole value you just calculated. Why do we do this? Because this mathematically forces the smallest component to become the baseline of 1, establishing the foundation for your ratio. Step 4, if your ratios aren't whole numbers yet, just multiply them by a suitable integer until they are. And step 5, write out your final empirical formula. Boom. When you understand the why behind step 3, I promise you, you will never forget this process.
All right, Section 3, mixing it up, concentration.
Let's take a minute to distinguish molarity versus molality, because honestly, these two terms are functionally completely different.
Molarity, spelled with an R, is the moles of solute divided by the total volume of the solution in liters. Molality, spelled with an L, is the moles of solute divided by the mass of the solvent in kilograms. I like to think of it kind of like a strict baking process. Molarity is like looking at the total volume of your cake batter inside the pan once every single ingredient is already perfectly mixed together. Molality, on the other hand, is like strictly weighing your dry flour on a scale before any liquids or other components are even added to the bowl. Make sense?
Understanding that functional difference actually leads us to a massive real-world application, because molarity is based on the volume of a liquid, and, well, we know that the physical mechanics of liquids cause them to expand when they get hot. Molarity actually fluctuates if the temperature or pressure in the room changes. A 1 molar solution in a freezing lab might actually not be a 1 molar solution in a hot warehouse. Crazy, right? But molality is based purely on mass, and since the mass of your solvent doesn't just magically change when the room gets hot, molality is completely unaffected by temperature and pressure. This is exactly why chemical engineers out in the real world strongly prefer using molality for industrial processes that operate in extreme environments.
Let's look at Section 4, Concentration Comparison Table.
Let's lock these three vital equations side by side into your memory. This is basically your ultimate cheat sheet. First up, we have mass percent, which is simply the mass of your specific solute divided by the total mass of the mixture, and then multiplied by 100 to get a percentage. This one is absolutely fantastic for solid mixtures. Second is molarity. That's denoted by a capital M, which is moles of solutes over liters of solution. This is your standard everyday benchtop chemistry unit. And third is molality, denoted by a lowercase m, which is moles of solute over kilograms of solvent. That's your temperature-independent unit. Keeping these three distinct in your head and knowing exactly when to deploy each one is absolutely crucial for both test day and your future lab work.
And finally, Section 5, beating the exam clock. Okay, you know the formulas and you know the deeper chemistry, so let's equip you with some practical battle tactics for those high-pressure exam environments. Trying to do complex multi-step stoichiometry math while you're experiencing cognitive fatigue? Well, it almost always leads to errors. So tip 1, take micro breaks during the exam. Seriously, just a few seconds to reset your brain and maintain full focus. Tip 2, in any reaction problem, immediately identify the limiting reagent. You already know this is the reactant that gets entirely used up first. But remember, exam writers specifically design questions to trick you into using the excess reagent for your math. Don't fall for it. Pacing yourself to find that limiting reagent early eliminates their most common trap. And tip 3, strictly track your consumed versus leftover amounts like a forensic accountant. Don't try to hold all those changing variables in your head. Actually write down given minus consumed right there on your scratch paper to keep your chemical ledger perfectly straight.
Which brings us to a final thought I really want to leave you with today. How do all these micro skills scale up from balancing a single simple equation on a piece of paper to engineering real-world chemical solutions? Well, mastering these precise calculations, from respecting significant figures based on actual instrument tolerance to knowing exactly when you have to use molality in extreme heat, it isn't just about passing some advanced test. It actually builds the very foundation for scaling up life-saving pharmaceuticals, designing incredibly safe industrial vats, and pioneering new environmental engineering. The massive world-changing solutions of tomorrow, they rely entirely on the exact structural math you are perfecting today. So keep optimizing your approach, stay intensely focused on the underlying logic, and I will see you in the next explainer.